Networks come in very different forms towards us. They come in terms of social networks, which kind of the best example of that would be Facebook, where it connects kind of billions of individuals together. But they also come as technological networks, where the nodes are routers and computers connected by physical cables. And these networks are also within our cells. How genes and molecules link to each other by chemical reactions and binding interactions and determine much of our illnesses and much of our future ability to really rationally cure a disease. So the challenge we have really in front of us is that if we are given this very complicated network, anything from the structure of the users and friendship connections in Facebook, all the way to the molecular networks within ourselves, how do we describe them? How do we think about it? What's the language we use to describe these complicated systems? And much of the early theory from the 1960s, thinking about complex networks, really assumed that these networks are randomly connected together. What do I mean by that? Let's start with a bunch of nodes that are originally disconnected, and with a certain probability we start connecting them. If you just add a few links, you will have a few pairs of nodes. As you are adding more and more links to the system, these pairs of nodes will connect up with other pairs, and then will eventually form pathways, and there will come a magical moment at which all these pathways will collapse together and will form a network. And much of the early thinking about complex network was that really networks are so complicated that the only way to describe them is to assume that they are random, that they are wired together as randomly as this image has shown earlier. What we learned in the last 10 years is something that you intuitively understand, that these networks are not random. They have fundamental organizing principles that hold them together. And what I'm going to try to do today is to share with you a few of them and move from networks towards human behavior. So I'm going to organize these things as more like laws. What are some of the fundamental laws of networks that apply very, very widely? And the first would be really the question of how the nodes connect to each other. A random network, a network in which the nodes are really randomly wired together, would look a bit like the highway system of the United States. And that's not entirely random, but visually would be very similar, where the nodes are the cities and the links are the highways between them. And the reason why a random network would be a bit like that is because this is a very uniform network. Most nodes have roughly the same number of links. You don't find hugely connected cities, or you don't find cities that have no highway connecting them to the highway system. And indeed, that's exactly what the random paradigm tells us. If people would be randomly making friends, most of us would have approximately the same number of friends. There would be no outliers. There would be no hugely popular people, and no one would be left behind. In contrast, about 12 years ago, we discovered that real networks look much more like the highway or the airline system of the United States or of Europe, where you have many, many small airports and a few major hubs that hold the whole system together. And these networks are called scale-free networks. There's a particular mathematical pattern that describes how they are connected together. But the most distinguishing feature of scale-free networks is the emergence of these major hubs. And these hubs are present in all different kinds of networks. They are present on the internet. This is a map of the internet at the router level, where nodes are routers and the links are the physical cables between them. And you can see a few major hubs holding the whole network together. They are present on the World Wide Web, as Amazon, as Google, as Yahoo, and major nodes that really hold the World Web together. And they are present in all kinds of social media that you perceive as a network. No matter where you look, if a network is emerging through some self-organized process, hubs will be there and will dominate your system. The question is, why do we have hubs? And that is really explained by what I'd call the second law, how networks really emerge. And there are two ingredients to most of networks that really govern how they grow and how they develop. The first is growth. No network emerges with 10 million or 100 million nodes without going through a growth phase. Growth means that you are always adding new nodes to the system. And the second is that new nodes don't connect randomly to the existing nodes, but they prefer the more connected nodes. You connect the nodes that you know, and you tend to know the highly connected nodes better. If you put these two ingredients together, you will see a process like that in which hubs will naturally emerge. This is what we call, the reason for that is a rich gets richer phenomena. When a new node comes into the system and it has a choice between the bigger and the smaller one, will more likely see and connect to the bigger one, and therefore the bigger node will grow faster. And this rich gets richer phenomena is really responsible mathematically for the emergence of the hubs. And what we learned in the last few years is that in every network where you have hubs, you must have growth and preferential attachment. This is that you must prefer the higher connected nodes. If any of these ingredients vanishes, your hubs will vanish, the network will not be scale-free. Now, the next question is, so what? Does it really matter that we have hubs in these systems? And the other conclusion that came out from this research is really, hubs really fundamentally change the behavior of the system. There are many examples of that. I'll show you one that I formulate as the third law, which really asks the question, how robust are complex networks towards node removal? What happens if your node breaks in the system? And if your network would be a regular lattice, like a square lattice, or a completely random network, we have the answers from the 1960s. They say, if you just remove a few nodes from the network, doesn't really matter, because you can route around the missing nodes. But as you start removing more and more nodes, you will always reach a critical point, and once you start removing more than the critical point, the network will fall into tiny pieces. That is, each network has its own intrinsic threshold. You cannot approach that. If you approach the threshold, you will destroy your network. Well, it turns out that's true for all networks except scale-free networks. Let's start from the network we built earlier and start randomly removing the nodes, and what you will see is the network simply refuses to break apart. And the reason is simple. If you are truly removing the nodes randomly, you will be removing one of those many small nodes, because there are many, many small nodes and only a few major hubs. Your chance of hitting the hub is very small. So therefore, you will shrink your network, but you will not destroy it. And indeed, we have mathematical proofs now to show that for a scale-free network, the threshold that you destroy it is 1. What does it mean? You have to remove all the nodes to break it apart, which also means that in a large enough network, you can remove 90% of the nodes, the remaining 10% are still holding together. But there's a price you pay for that. And the price is, what if you don't remove the nodes randomly? What if you go on an attack, starting with the biggest node, then the next biggest node, and then the next biggest node? And not surprisingly, the network will very rapidly fall apart. Look at these two networks. On the left-hand side, I removed 25 nodes. On the right, I removed 8. On the left, they're still together. On the right, are broken into tiny pieces. This double property we call the Achilles heel of scale-free networks. They're very robust to random failures, but they're very fragile to attacks. Once you know how your network looks like, you can very easily destroy it. What I would like to do next is to give you an example how some of these ideas lately are being used, for example, in organizations, a system that we're all familiar with. So let's look at this particular company. This is a kind of a small company in Hungary with about a few hundred employees in 3 different locations, and this company had a major communication problem. Simply, whatever the higher management would decide, not that that decision would not reach the workers. Often the opposite news would be traveling within the organizations. And I'm sure you have encountered similar situations. And the question is, how do you find out what's going on? What are the missing channels of communication within the company? And you do so by building a network, by asking each individual, whom do you turn for advice when it comes to company matters? Whom do you ask them? Who do you chat with on a regular basis, where you get your jobs and whom you delegate to? And those simple questions, which are very non-intrusive, will actually turn this company into a network. And you suddenly start seeing the hubs. Because some individuals naturally emerge as being the center of the company, and they are not hubs because they told themselves about being hubs. They are hubs because lots of people pointed to them as being the source of their personal information. Now, you would hope that these guys would be the people that should be the hubs, which is the higher management and so on. I lost my screen, or there we are. And so let me actually show you where the higher management is. So those are the red nodes. Do you see any red hubs? Those are the CEO and the directors. Unfortunately, none. Well, the top management is the blue guys, and unfortunately, all the blue guys are really tiny on this map. And you have a purple, which is a manager, and the real biggest hub is really that gray fellow, which is an associate, a very graceful way to say an ordinary employee. And that person is about 2 degrees away from everybody else within the company. He is the source of information within the company. All the information is really traveling to him. Now, who is he or who is her? Well, we know that. That person is actually the health and safety responsible individual within the company, the only person whose job is to go from group to group and talk to everyone on a daily basis. He picks up information and passes on over there. He has links to everyone except the higher management. So he is really the gossip center, and then you would ask, what do you do in this case? Do you fire him? Is it his problem? No. He is really filling in naturally through his personality and his job a structural hole that is naturally there in the company. The best way to solve this problem, talk to him and 4 other guys. Tell him what's going on, and soon enough, the whole company will know what you really have in mind. So this is one way how you can actually use networks, and there are many other examples from biology to technology. But let me switch gears very briefly and talk about another aspect of our life, which is human decisions. And I'm going to talk actually here in particular about human mobility. This is Paris at night. And you can see how people move around because they carry cell phones. And once you carry a cell phone, then your company needs to know where you are. And when these cell phones fly in the sky, it doesn't really mean that people are throwing their phones up in the air. It just means that so many people moving in that neighborhood, there was no way of showing them that mass without taking them out of the plane. But the bottom line, what I'm showing you, is that because we carry cell phones and many other devices, our behavior can be tracked in a very objective manner, and we can start asking quantitatively, how do we really behave? And in behavior, I will look momentarily at human mobility, because that's one of the most important behavior forms. Where you are determines what you do. If you are at a conference, you chat with colleagues, you meet new people, you listen to talks. If you are at a bar, a completely different scenario. If you're in an office, you have another activity. So if we understand how people move around and what is determining it, we understand a lot about human behavior. And thanks to data like this, we can actually now quantify how people move around. One example of this quantification is to look what are the distances people travel on a daily basis, finding that, not surprisingly, most people travel very little, 2 to 5 kilometers on a daily basis, and a few individuals travel hundreds of kilometers. That is not surprising to anyone. What is interesting is that the number of people who travel 200 versus 5 kilometers is very fixed. So you don't think about what everybody else is doing, but we are all part of a major distribution that can be very precisely mathematically described, even though we take our decisions individually, together we are very predictable. And that together predictability has very major consequences. It helps us, for example, predict diseases and the spread of diseases. This is a colleague of mine, Alessandro Vespignani's work from 2009, where in spring of 2009 predicted the full run out of the H1N1 epidemic. And no one really believed him back in that time, because he told the epidemiology community that the H1N1 virus will peak out in October and that the November vaccine will be way too late. He turned out to be completely right on that. And what is this really showing is, because we have very predictable global mobility patterns, we can very accurately predict how many people will get sick in every city around the world, on a weekly basis. And the studies actually show that that was like really within 10% accurate throughout the whole period. So this is what I call global predictability. Our global mobility patterns follow very precise mathematical laws, and as a result, things like virus spreading can be predicted. But how about at the individual level? Could you predict, or could someone predict where you're going to be tomorrow at 3 p.m.? And that seems to be much more difficult. And the reason for that is because the mobility patterns of individuals are so different. So here you see the mobility patterns of two individuals. The fellow in the left, in the 2-week period, traveled in about a 20-kilometer range. The fellow in the right traveled about a 100-kilometer range. So you see a huge degree of population heterogeneity. We are different from each other. We behave in a different manner. We go to different places and vastly different number of places over the same amount of time. Yet, despite this diversity, there's a huge amount of predictability even in the individual motions. And the way to extract that is we simply start looking where this, for example, the left individual is on an hourly basis. We use mobile phones for that, and unfortunately, we don't know the location of the individual when he or she doesn't use the phone, so we know only when they use the phone. So these are the colorful bars telling us what is the location of the individual during the week when he or she uses the phone, and when there is no color means that we have no idea where they are. So it looks like we're missing most of the data, but we have this data for months and years into the past. So I should show this way. And by having so much data, even though the data is incomplete, we can actually infer what we call the entropy of an individual. That is, we assign to each of you, to each individual in our data set, effectively an entropy measure. Why do we care about entropy? Well, because entropy really tells us about randomness and, to a certain degree, predictability. A system's entropy is 0 if it's completely ordered. There is no disorder in the system. And the system has high entropy if it's disordered. And entropy is deeply linked to predictability. So go back to this configuration and remove one node. And you know exactly where the node is missing from. It's extremely predictable because the entropy is so low. But if I'm going to remove a node from a system that is in a much more disordered state like that, you're going to have serious difficulty predicting where that node is missing from because the entropy is high. So therefore, if I can measure your entropy, I can assign to it your predictability, and that's exactly what we did for each of the users in our data set. And so now we have for each individual a measure of predictability. This is pi, and your predictability is 0 if no matter how much data I collect about you, I will never be able to tell where you're going to be tomorrow at 3 p.m., which means for all practical purposes, your mobility is random. Your predictability is 1 if I collect your hourly location the next 3 months, I can be 100% accurately predicting your future location. And what you see, this green curve, is really the distribution across the many tens of thousands of individuals we measure this data for. And here's what we find, which is interesting. We find that most people have a 93% predictability. What does it mean? It means really that if I get access to your past locations with 93% accuracy, I can tell you we're going to be tomorrow at 3 p.m. And that means that out of 100 trials, about 3 times I will actually fail, 7 times I will fail, and 93 times I will get it right. Most surprisingly, there is no one under 80%. And that was really shocking to us because we thought, hey, you know, I am very regular. I work in the same coffee house every morning. I go to the same place to have lunch. I have a terribly regular pattern, but there's this cool girl next door with pierced ears and pierced nose, and she's cool and she's spontaneous. And yet, the data is showing no one is really under 80%. And the measurements indicate that indeed a colleague of mine at MIT has looked at the MIT students, and you would think that if there's any group of the population who should be spontaneous and unpredictable, they should be the students. And yet what we find for the MIT students is that there was a 95% predictability, and the remaining 5% was only Friday and Saturday night. The rest of the week we were 100% accurate. So yes, doesn't mean that we don't have free will. It's just that we don't really use it in the way we think we do. And you know, when it comes to their daily patterns, we're terribly boring and we're terribly predictable. So down the line, the question is, why do we focus so much on human mobility? It's not that I really deeply care about mobility, but mobility is one of the cleanest way of measuring human behavior because we can objectively say where you are. You are either here or you are not here, and you know, and we don't have to turn to you to ask you where you are or how you feel about it because there's an objective measure of location. But we think of this one as being a model for most other behavioral patterns. And it's not that we think that other behavioral patterns will be actually 93% predictable, but what we claim is that you can assign to most behavioral patterns a number telling us how predictable it is. Could I predict when you're going to fall in love? Maybe. with a certain percentage, may not be 93%. Could I predict when you're going to meet an interesting person? Again, with a certain probability could be predicted. So down the line, we can take with time, if there's enough data, all type of different human behavioral patterns and quantify it and look at the predictability. And you can imagine, probably much better than I do, what are the potential applications of that approach. So in summary, I try to tell you about 3 different things. First, about networks, which is asking with whom do we interact with? And the answer, mostly with hubs and others similar to us. There's also another aspect of that. And network science aims to describe the structure of these networks on which we're all part of and determines our ability to get things done. Where do we do that? Well, mostly nearby. The vast majority of people hardly move at all. They're staying nearby because we really rarely go too far, and human mobility is really trying to capture that. And the question is why? That is because we did it yesterday, and we're going to do it tomorrow and the day after tomorrow. We're terribly predictable because we are regular. We don't like to admit it to ourselves, but much of our daily patterns are really routines and routines and routines. And I think routines are wonderful, and they're great, because they free up emotional and intellectual time to think about great things. But down the line, once we put it down to number, we are routines and we're predictable, and that has lots of consequences to lots of different industries, as well as to understand what we do on a daily basis. Thank you very much for your attention.